As an example of how to balance a binary search tree, I would like to show you red black trees. So why do we want to balance binary search trees? Binary search trees are an important data structure for dynamic ordered sets. They are very versatile, but their running time depends on the height of the tree. Now, in the worst cases, height could be very bad, but not if the tree is balanced. And that's what balancing is about. We want to make sure that the height of the tree at all times is of order log n, because then all of the operations that we want to have, we get in this time, and that's very efficient. What is a red-black tree? A red-black tree is a binary search tree where every node is colored either red or black, and we have some additional properties. So here we have an example of a red-black tree, and the properties that we want to have is, first of all nodes should be either red or black. Then we also consider the nil node, so any node which stores a key has two children, and these children might be in Python a none, or as here I will describe it, a nil. And in our setting now we will consider these as parts of the tree. So normally when I say a leaf of a tree, then I mean a node where both children are none. Now I'm also taking these none children as parts of the tree, so now my leaves are these none or nil nodes. And these should be black. Then also the root of the tree should be black. And now if I have a red node somewhere, like the 18 here, then its two children should both be black. And the final property is that if I am at a node, any path to a leaf should contain the same number of black nodes. So if I'm here at the 18, then if I go 2 steps to a leaf, and that's why we need these nil nodes as leaves so that this counting works. This is 2 steps, but if I go here, it's 3 steps, but it's 2 black nodes. And here also 2 black nodes, 2 black nodes, 2 black nodes. All paths to a leaf see 2 black nodes for this 18, and in general we want to have that for every node. All paths from that node have the same number of black nodes. We call that then also the black height of that node. So generally the height of a node is the length of the path from that node, the longest length from that path to a leaf, so the number of edges on that path. The black height now counts only the black nodes on that path, not counting the node itself if it was a black node. So let's do some examples. So if we take, for instance, a 50 here, then a path to a leaf contains 1 black node, namely the nil node. And again, because of property 5, all of these paths have the same black length, so the black height, I can take any of these paths. So the height of this node is 1, because with 1 step I'm at a leaf, and also the black height is 1. Now if I take the 18 here, the height for the 18 is actually 1, 2, 3, but the black height is 2, because with 2 steps I'm at a leaf. And even this very long path, if I follow that path, there are 2 black nodes. And as last example, if we take here the root, the 10, then the height of that is 4 via 18. The black height is, just as for the 18, 2, because to a leaf I see 2 black nodes, not counting the 10 itself. So that's the black height of a node. So you may wonder, why do we need to have these nil nodes as nodes of the tree? So this is for counting. So property 5 is necessary to bound the height of the tree. And to formulate property 5, it's very convenient to have these nil nodes, because then I count this path here as a path to a leaf. Otherwise I would have to say a path to a nil. When we draw a red-black tree, we're going to draw it without these nodes. But keep in mind that in principle they are there, but they're just there to count black paths. So let's first prove that if we have these properties, that indeed the height of the tree is bounded by order log n, specifically by 2 times log n plus 1, where n is a number of internal nodes, so the nodes with keys. And for this, the black height is very important, because what we have here is that if I have a node x and I know its black height, it tells me how many nodes I will have at least in the subtree. Namely, I have at least 2 to the black height minus 1 internal nodes in the tree rooted at x. Why is that the case? Because every path to a leaf has the same length. So the smallest subtree which could achieve this is a tree which only has black nodes. And that would be a complete binary tree consisting of black nodes. It has black height x. So how many nodes does it have? As x is 1, then 2 underneath, 3, and so on. The last level with internal nodes is black height of x minus 1. If I take the sum, so if I take the sum I from 0 to black height minus 1 of 2 to the I, then this gives me 2 to the, we have a geometric series, black height minus 1 plus 1, so that's simply black height of x minus 1. So for instance, 1 plus 2 plus 4 is 7, which is 8 minus 1. So that's what's going on here, and that is this bound over here. So now I have a guarantee on how many nodes I have at least in this tree. That means overall I have this number as a lower bound on n if I take the black height of the root. So I look at the black height of the root, I know the tree rooted at the root, which is a whole tree, has at least this number of nodes, meaning that n is at least this number. Now taking logarithms, I get that the black height is smaller equal log n plus 1. I take the minus 1, bring it to the other side, and then take logarithms. Now I know the black height is bounded by log n plus 1, but I wanted to bound the height. So how big is a height compared to the black height? So now we can use a property that every second node on a path has to be black. So the height of a tree is the length of the longest path to a leaf. Every second node on that path needs to be black. Therefore, in particular also the last one, the leaf. Therefore, we have that this path length is bounded by 2 times the black height. 2 times the number of black nodes on the path, because every second one is indeed black. So the height is bounded by 2 times the black height, and we have that the black height for the root is bounded by log n plus 1, and this proves our statement. So now we know that red-black trees, if we can maintain them, they indeed are balanced. So they indeed give us this height of order log n. So let's see what happens when we insert into a red-black tree. So here we have a red-black tree. Again, I'm not drawing the black nil leaves. So how do I insert? I just do a regular insertion. I make the new node red, and then I fix the red-black properties. Let's look at an example. Let's assume I want to insert the 15. So a regular insertion would do a binary search, or do a search in this tree for the 15. So it's larger than 10, it's smaller than 23, it's larger than 12, it's smaller than 17. Now I know where I want to insert the 15. So now the 15 is inserted as a red node. So I have step 1, I have step 2. Of course, the 2 children again are black nil leaves. Now I need to fix the red-black properties. So which properties might be violated? Let's have a look. Every node is either red or black. That is true. The root is black. Okay, this is most likely true. If the tree previously was empty, then I just have this one node, which is red so far. This would be very easy to fix, but this might be violated. Every nil leaf is black, so sure, that is the case. I again make see the nil pointers of this node as being black. If a node is red, then its children are black. So this definitely might be violated, and this is something we have to take care of. Last property, the length of any path from a node to any of its leaves has the same number of black nodes. This is still the case because the only thing that we changed, we added a red node here. So previously there was a black nil leaf there, which I replaced by a red node with 2 black children. This does not change the number of black nodes on any of the path. So what we have to deal with is property 2 and 4, and in particular 4. I mean, 2 is easy, but 4 might be a problem. And the way we're going to do this is with so-called rotations and then also recoloring. So what is a rotation in a binary tree, particular binary search tree? Let's assume this is a valid binary search tree, then I can obtain a search tree, a valid binary search tree with the same keys in the following way, and this is called a right rotation. So I take the node X, kind of pull it up. What do I mean by that? I make Y, which previously was a parent of X, I make that the child, the right child of X. And now I have to attach the right subtree of X somewhere else, but I can now make it the left child of Y. So assuming that X was a left child of Y, I can now make the subtree, the right subtree of X, the left subtree of Y. So you see, this tree has exactly the same nodes, and if I check the binary search tree property, if it was true here, it still holds here. So that is a right rotation. If my parent is to the right and I pull it around like that. There's also the left rotation. This is a setting where, so here if you look from the perspective of Y, X is now the parent and it's to the left. I can now also rotate, so that's simply here the inverse, pulling Y up, bringing X down as a right child, as a left child of Y, and obtaining this tree here. So this is a rotation in a binary search tree. Rotations will help us to fix a red-black property. So intuitively, and this is just one of the cases, what will be happening here is, so let's assume both of these are the red ones. This one has to be then black. Then if we rotate, we can instead make Y red, keep this one as red, and this will allow us to make X black, and then this way we store the red-black property. So what did we see here? We moved this middle tree through the rotation to the other side, allowing us to recolor the top nodes here, which allowed us to get rid of the violation of the red-black property by now having a black node and then 2 red nodes. So we have a violation of the red-black property, and we want to solve it using rotations and recolorings. And here's how we're going to do it. So what we're going to do is we're going to maintain the following invariant. So we have this violation, so Z and P of Z, those are both red. But I'm going to assume that this is the only violation of the red-black properties that I overall have in the tree. And the general idea now will be that I kind of move this violation up the tree until it either simply disappears or I hit the root. But if I hit the root, so if Z eventually is the root and it's red, so at this point it doesn't actually have a red parent, then I can simply change the color to black, and I'm done. So while I'm doing this algorithm, I can assume that I have these 2 nodes Z and P of Z, they're both red. So as long as Z is not the root and it has a red parent, and this in particular means that the parent is not yet the root, because I know by the red-black properties that the root is black. So as long as I have these 2 red nodes and then the grandparent is black again, obviously, I'm now making a case distinction on whether the parent of Z is a left or right child of its parent. So let's assume the parent is a left child of its parent, and the other case will be symmetric. Now I have the situation, the parent is a left child of its parent, that one is black. Now let's also look at the other child of that parent, so the grandparent of Z. Let's call that Y, and let's assume that is also red. So that will be the first case that we solve. So it looks like this. What can we do? So we have this violation here, which we want to get rid of, and our strategy was to bump it up the tree. We can do this here simply by recoloring. So what we're going to do is we're going to make the grandparent, so the parent of my parent, I'm going to make that one red. I'm going to make y and the parent black. And in this way, this violation went away. Now, of course, I could still have a violation further up the tree because the parent of the grandparent might be red. So now I might again have two red nodes. So what I do now is I make this grandparent here, I make that node, the node Z, and I continue my algorithm there. So I continue my while loop, but now with this node as a node with a potential violation. So this was case 1, where the parent and the other child of that grandparent both were red. This leaves 2 cases to do, and in both of these cases now y, so the other child of the grandparent, is black. And now our case distinction works as follows. So let's assume that Z is a right child of its parent. So I'm in the situation Z sits here. This is the parent, this is a grandparent, and as we said, y is black. So now we do a left rotation around A, so around the parent. What do we get? We get that now Z sits here, A is down here, and we still have the violation, but now instead of Z and A, we have A and Z. But more importantly, I have this violation now with the child. So let's make A our new Z, is now the left child of the other red node. So I reduced the case where Z was a right child to the case where it's a left child. So now let's focus on this case here. What I'm now going to do is I'm going to rotate around B like this, and I'm going to recolor. So Z moved up, A is now here, B is down here, and I now recolor the 3 nodes here. And if you look at any path to a leaf, the number of black nodes along such a path still stays the same. So if I come from up here, then I won't notice that Z is a black node and these are red, versus previously having B as a black node and these being red. And if I'm below, also the count of black nodes to leaves stays the same. So now in this way I have all of the red-black properties, and because I now have a black node here, I know there are no further conflicts. I am done. Perfect. I fixed the red-black property. Let's look at this by example, and the example is the one that we already saw, where we just inserted a node, the 15 here, we colored it red. So now we have a violation because we have a red node and its parent, the 17, is also red. So what do? We look at the grandparent. The grandparent is a node 12. Now 17 is the right child of 12. So that's not the case that we previously saw. There we had the left child, but the case is symmetric. And now we can look at whether we are in case 1, 2, or 3. For that, we look at the other child of that grandparent, y, and this child is a nil leaf, so that is black. So we're not in case 1, where this one was red, but in the cases where it's black. And now the case distinction is whether the 15 is the left or right child of the 17. So because it's the left child, we first have to do a rotation around the 17 to make it the right child. And the reason for that is because then we can do the rotation at the 12 and fix the property. So we do a rotation around the 17. Now 15 moved up, but more importantly, the pattern of the red nodes is now in line. So the 17 is the left child of 15 and 15 is the left child of 12. This brings us into the case 3, where we can do a rotation around the grandparent, so around the 12. That looks like this. Now the 12 sits here, and now I can recolor the 15 black, the 12 red, and the red-black property holds. So let's recap what happened here. So we have these 3 steps, and the interesting step, of course, is fixing the red-black property. How did we do that? We move up in the tree as long as case 1 occurs. And case 1 was where the other child of the grandparent was also red, and we have to recolor, and in that way the violation might move up the tree. If we don't have case 1, then we have case 2 or 3. Then we need to do at most 2 rotations, and in that way can fix the red-black property. So what is the running time of all of this? So moving up the tree, that takes constant time per step, and I do this at most height of the tree many times. Then I have 2 rotations. A rotation I can do in constant time. So what does this give me overall? As running time, I get order height of the tree. And that is, because we have a red-black tree, order log n. Now deletions work in a similar way as insertions. So I do a regular deletion and then I fix the red-black property. I just wanted to give you an impression of red-black trees, so I'm not going to cover deletions in this video, but the principle is the same. So you again use recoloring and rotations. You have a slightly more involved case distinction, but it goes through, and with the knowledge about recoloring and rotation, it's easy to read up on it if you want to. Overall, we are going to use recolorings and at most 3 rotations for deleting an element. This means we can insert and delete while maintaining the red-black properties, and that in particular means while keeping the height of order log n. So this means that all of the operations that we want to do, like search, insert, and delete, but also let's say maximum, minimum, we can now all do in order height. And because order height is order log n, we can do all of these operations efficiently in order log n time. And that's all that I wanted to say about red-black trees. See you next time.